Right. Why are graph neural networks so rare when modeling for protein design? I'd like to start out by just describing my personal background with machine learning. Um, so here I'm just plotting my timeline at the end of UNC in the Coleman Lab, and then my new job at Menten AI. And at UNC before AlphaFold, very little bit of machine learning here and there, but it was a low fraction of my of work. And then, like a lot of you, once AlphaFold comes out, it just shoots up. And then ever since then, machine learning has been a big part of my life. This is all just to say that I'm not an expert or been doing this a long time. This talk is going to come from an application perspective. I mentioned this just because I think a lot of us are in the same boat because this curve also kind of matches the number of machine learning talks at these Rosetta conferences. So I think AlphaFold inspired a good number of us to kind of follow this pattern. And when we have these machine learning projects, one big question we always have to answer is how should I represent my protein in my tensors? Something we've seen a lot of lately, both for input and output for neural networks, is a contact map, where you take you lay your protein sequence end to end on one axis against itself, and then the residue pair distances are plotted in the within the matrix that those two axes form. That's one option. Something else we've been seeing lately is 3D voxels. Just take the XYZ coordinates of all your atoms, assign them cubes in space, and then you can run just the equivalent of an image analysis network, but just higher dimensions in 3D instead of 2D. This talk is going to be talking about graphs. This is something that some of us are very familiar with, some of us maybe not so much. The idea is that each residue in your protein has its own little node in the graph. I stole this from actually a Rosetta paper, so some of these names might look familiar. So each residue has a node in the graph, and then residues that are close in 3D space have this edge as a connection in the graph. So why is this so great? The big thing is that the user can customize locality. So for example, contact maps, the locality of a convolution when you analyze it is defined solely by sequence. And residues that are close in sequence space will have close locality in a contact map. But with graphs, you can define whatever locality you want. This talk kind of assumes that you're doing some sort of spatial locality where residues that are close in space have edges, but it could be anything. So that's the bonus of graphs. Just as an alternative to contact maps where your sequence defines what other residues you're close to. Another big benefit is orientation invariance. If you take a protein and rotate it 90 degrees in space, to us, it's the same protein, and to graphs, it's the same protein. But in 3D voxels, it's different. At least you don't get the inherent invariance of being able to do this. You need to do data augmentation to account for that, and it's just a larger challenge. You can also run into problems. You can imagine if you nudge your protein slightly to the right, then some of your atoms will move into the next voxel while others will stay in its original voxel. And again, it's the same protein, but just the voxelized form will represent it differently. So it's noise that we don't need. My biggest thing, though, is that we love graphs in Rosetta. This is a list of just a few graphs that I found in the Rosetta code base. And for us on the C++ side and in developing Rosetta, the graph is really where you start. It didn't take much convincing for me to say that I should be trying to do machine learning with graphs, because it's really the starting point in most of our protocols, that when you're working with residue interactions and you have a known structure, graph is the way to go. So why don't we see these so much in machine learning? They're not terribly rare. Like you do see them. It's just not as common as the previous slide would have led you to believe, though the frequency is increasing. So this talk, I'm going to lay out a few reasons why they might not be seen so much. and then we'll talk about solutions to those problems. So the three hurdles that I laid out is that they're new. These graph convolutions just aren't as mature and developed as things like image convolutions. There's a lot of bookkeeping. So these graph networks can be tedious to work with. And training is tricky with these. So I'll talk about all of these more, but this is just the outline of the talk. And we'll give quick solutions for each of these. Problem one is the simplest because there's not much we can do about it. Graphs are new, graph neural networks are new. Like I said, we have seen these, but you have to be like Vlad. You have to be super smart and create your own, kernel in the code to be able to run these. You can't just, load in a package and just run a graph neural network until just 2 or 3 years ago. So the tooling is only now catching up. I highly recommend the Spectral library. It's maintained by Daniele Grattarola, who will come up later because we're working with him to solve problem 3. There's this huge menu of different operations you can use in Spectral, 17 convolutional layers and counting. There's pooling layers. He helps manage the data for you. And I think Spectral has one of the best URLs out there. It's graphneural.network. So there's no real solution to problem 1 because, we just have to wait. But in the meantime, Spectral is great for beginners. It's a very mature package, and I highly recommend looking into it. That's the quick one. 2 and 3 are going to be a little bit longer. Number 2, GNNs are tedious to work with. Graphs are a little bit tricky to represent as tensors. To represent a graph, you need 3 tensors. You need an adjacency matrix. You have the X tensor, which holds node data, and then the E tensor, which holds data that resides on the edges. And not only do these A, X, and E, they all have to be perfectly in sync with one another, but they also have tricky dimensions. When you add and remove attributes, you have to adjust the dimensions, but also just quick optimizations, well, that would normally be quick, are really tricky with these tensors because you would change dimensionality if you want to do a dense or a sparse representation of your graph. And there's a lot of bookkeeping. None of it is a terrible hurdle. People overcome it, but it's enough to discourage newcomers from even getting started with these graphs. It took me a while to get past this because there's just so much that you have to be sure of. And, if you mess one thing up, it's really difficult to tell. So the solution is Menton GCN. And, I work for Menten AI. So Menton GCN is something that we created to really approach this problem. This is a Python package that takes a Rosetta pose as input, and then as output, it does all of the bookkeeping and work to give you the XA and E tensors that you can then run through your model. And it doesn't do all of the training for you, it just does the marginal work between normal machine learning and graph machine learning. So it keeps track of nodes, edges, what data goes on them. It computes all of the data for you from the pose, and it's pretty extendable for you to create your own attributes. The documentation is live. We have a readthedocs.io. You can install it pretty quickly with pip. And this is an open source project on GitHub, so feel free to check that out. Collaboration and bug reports are always welcome. The general idea, this is a little bit of slideware. You would create a data maker from the Menton GCN package. And when you create it, you would specify what type of data you want on your graph. So in this short example, your graph would one-hot encode your amino acid sequence on your nodes, and then there'd be hydrogen bonding info on the nodes and edges. There's a full menu of different decorators that you can use to put on your graph. You feed this into a data maker. You then give your data maker a Rosetta pose, and it returns your XA and E tensors. Everything from here on out is just machine learning as normal, which isn't to say it's easy, but it's it's not extra work to deal with graphs. One thing that I really like about this, and we made a priority when making this package, is that it's easy to share. Anybody can make the same data maker, and when they run their Rosetta post through it, they can make the data that works for your neural network. So if you send your neural network across the country, they can pretty quickly create a script that can run their post through it. Building on that, there's also a sub package where when you use this and you publish and you want to share your model, you can just create a data maker in this library. So if Daniele and I create a 2021 paper and publish a model, that'll be included. You can just create a data maker from the package directly, run your Rosetta pose in there, and then you automatically have the tensors to run whatever model is associated with this data maker. That's all just to say that this is trying to do the bookkeeping for you. Collaboration is welcome. So feel free to try this, and please reach out if you do. Before I go on to problem 3, I want to quickly describe what happens under the hood of a graph convolution. It works by, traditionally graph convolutions work through message passing. So say just for the sake of example, we have some data on this node here. Then when we run a single graph convolution, that data can only spread it can only traverse one edge. So it can only spread this far. So if we want to go farther, we would need a second layer. If we want to go farther, you would need a third and then a fourth if you want your data to get that far. This is all a little bit hand wavy, but this is all, the point of this is to show that there's some benefit to depth. Now you can get around this by just creating longer distance edges. The trade-off there is that it's more challenging to train your model because then your model has to learn, well, which edges should I be ignoring? It's just more noise in the system. So that's a very quick precursor into problem 3, which is that GNNs traditionally, and this is an oversimplification, but they're not great for deep architectures. It's possible, but challenging to go deeper than 2 or 3, especially in our world where we have data on our edges. And even the experts in the field recommend just sticking to maybe 3 or 4 or 5 layers. So this can be a problem for large proteins because it'll take a few convolutions to recognize patterns and then a few more to propagate those patterns to the neighborhood, and then a few more to deal with that data. So, 2 layers is very limiting, space to work in. Additionally, the field just isn't quite developed for our type of graphs where we have, not only do our nodes have a lot of attributes, but so do our edges. And this is different from the likes of a social network, for example, where GNNs are traditionally used, where on Facebook, if each human or user is a node, then an edge is relatively simple. The simplest is it's either there or not, or it might have some simple data, how long have these 2 people been friends on Facebook, but it doesn't have the advanced geometric relationships that we model when evaluating residue pairs. The solution I'm proposing for this is also a little bit self-involved, but there's this new convolution XENet, which we made in Menton with the help of the spectral maintainer, Daniele. That'll be, the preprint will be out in a few weeks, along with as well as Menton GCN is inside that. This layer consistently gives us better validation loss, which is the main goal of training. But it's also more robust for deeper architectures. The formulation itself I won't go into because we're a little bit short on time. The gist is that this convolution pays a lot of attention to what's on the edges, the actual data on edges, instead of treating them like second-class citizens like other convolutions do. And it just seems to work for us. This is a big claim to make, so I am gonna do a rapid use case. Forgive me if I skim over something because it's a lot to fit in. So we use this convolution to analyze a residue on a backbone, a residue position, and predict which rotamers are worth sampling during the packer. So just a quick gist, we have this protein core redesign, 10 core residues, all 20 amino acids using the Q packer, the quantum annealer. We are using 3 different candidates to train the neural network. So XCNet is what we came up with, and then the other 2 are established in the field for this type of use case. The idea is the input to the neural network is a graph representing a single residue's environment. The output is just some form of which rotamers should be sampled and which shouldn't. The data looks like this. So the control, we have the fraction of rotamers kept. So if you don't do any machine learning, you have all of your rotamers. And the y-axis is, well, when you run the packer with this rotamer set, what's your score? So with no machine learning, negative 158 Rosetta energy units. And then as you use the model trained with XCNet, you can get down to about 60% of your rotamers before you see a drop in quality. I hope this is a little bit clear. What we're progressively changing the cutoff in the classifier to say, well, how many rotamers can we remove? And so that's why there's multiple points. And as we make it more and more aggressive, eventually we cut rotamers that are valuable. Compare this to the other 2 candidates. So the crystal convolution and ECC are the 2 that are established in the field that we tested against. And they do almost as well. XCNet does, so left is better here because it means we can eliminate more rotamers. And we're mostly looking at these vertical lines. XCNet does outperform them. The margin of victory is relatively modest. The real win wasn't how deep we can go. So we tested all of these with different layers. After 2 layers, the ECC and the 2 that are in the field, they failed to train once we added that 3rd layer. But XCNet succeeded all the way up to 5 where we stopped testing. So even though, since this is just measuring small pockets, there's not a huge need for deep models, but hopefully this means that when we run XCNet on a large protein, we can get more advanced message passing patterns because we can go deeper. Quick summary, problem 1, GNNs are new, tooling is rare. I recommend Spectral. I think it's the best library out there for it. Daniele, the maintainer, really knows what he's doing. But the real solution is really just wait as tooling evolves because the field is growing. Problem 2, GNNs require a lot of bookkeeping. They're tedious. I'm really hoping Menton GCN can grow into a solution for this. It works for us, but that doesn't mean like, you know, I hope that it'll work for you too. And if it doesn't, please let us know. But it is, it's hopefully it can fill that role. Problem 3, GNNs can be fragile for graphs like protein structures where we have a lot of edge data. I think XCNet is a really good solution for that. That'll be in Spectral in a few weeks when our preprint comes out. So that's kind of the quick summary of everything we covered. I am going to do a little bit more of a in-depth talk about all this in an upcoming Vlimlar, which is the speaker series I mentioned at the beginning, so that we can talk about this in a less rushed way. But with that, I'd like to say thank you. Half of this talk was about work that Daniele's